One of the other kinds of imaging works by emission. And what happens in that case is we introduce some kind of radioactive material into the body and we track the decays by looking at what comes out of the body. The oldest kind is called single photon emission computed tomography, or SPECT. This is related to positron emission tomography, or PET, which you probably have heard of even if you haven't heard of SPECT. One of the big steps here is development of drugs. You have to find a way to get something radioactive, which generally means some kind of heavy metal. You have to find a way to convince the body to take it to the area that you want to image. So if you have something that cancer cells take up more than good cells, that would be a drug that you want to tag with something radioactive. One of the most common of these is called cardiolite. That's a trade name. And what it does is it takes radioactive technetium-99 to hungry tissue, and that is your heart or cancer cells. Millions of people every year get scans with this. If you know somebody who has had chest pains and the doctor has them come in and do a stress test, ride a bike or walk a treadmill or something while they're imaged on either side of that, this is what they're getting in almost all cases. So the radioisotope gets taken to the area of interest, like the heart, and it decays. And for this technetium, the half-life is about 6 hours. The decay for this is almost always a 140 keV gamma ray. This gets picked up by a sensitive crystal here, sodium iodide, that turns that one gamma ray into many, many visible light photons. These red things here represent photomultiplier tubes, or PMTs. These are a super accurate way to turn light into electrical pulses. So it's kind of like an electric eye looking at the crystal for these pulses. And by looking at, was the flash closer to this PMT than that one, you have a better idea of where in the crystal it actually was received. Now, we still need collimation for this. The problem is we can't start out with photons being collimated. They're going to be emitted in all directions in the patient. And what's going to happen is most of them are just going to get blocked by this collimator here. Some of them that come straight out and go down the lead honeycomb, they'll be detected, but this, like this blue one, should get rejected. The thing about this, one of the big problems here is efficiency. Out of all the photons that get produced in the patient, fewer than 1 in 1,000 of them gets to the detector. So lots of them go, over here where there's nothing to see, there's nothing to catch it, no detector or collimator or anything. Some of them are going to hit the sides of the collimator. Some of them will scatter, but very, very few of them will actually get imaged. And that's going to lead to the big problem with this compared to CT. If we look at a picture of a CT scan below, it looks kind of like somebody sliced open a person and took a 35 millimeter camera and took nice pictures of the inside. Below that is a SPECT image of the brain. And if you look at this, it looks more like something you would draw with a crayon in your foot. If they're both using photons of about the same energy, why are the qualities so different here? This is much sharper in the CT, and it's just horrible in the SPECT. One big question, or one big reason for this, is having the incoming radiation collimated makes a big difference. The X-rays are all going, let's say, left to right parallel to the floor. If you get an X-ray that's not going that way, it had to be scattered, so you get rid of it. So you use the collimator to block it. But you can't do that with SPECT because the gammas are coming out in all directions. So you can still have a collimator, but it's going to remove far more photons than is in the case of CT.